Hello. Hello.
Hello.
Hello. Hello. Hello. Hello.
Hello.
Hello.
Okay.
Okay. Okay, so I suppose I am audible loud and clear. So this is our NPTEL live session of week 8 for the course of non-conventional energy resources taught by Professor Prathap Haridoss from IIT Madras. And I am Lalit Bharti, a Prime Minister Research Fellow in the Department of Physics at IIT Kharagpur. I am taking these NPTEL live discussions for this course. So today we'll start with the syllabus of week 8. So this syllabus is according to the lectures available on this NPTEL website under this course. So basically under week 8, we will be discussing on wind energy. And in wind energy, we will be specifically taking the topics of wind energy efficiency. We will see the efficiency factors. How does it affect? Then we will cover wind energy parts and materials. And then at last, we'll cover this design consideration part. So mainly we will be taking problems and questions on these three topics. So we'll discuss this year questions and previous questions, all relevant to this week 8 syllabus, which will be helpful for your main exams and understanding this course. Okay, so we have this question. These questions are basically from your non-graded assignments or available on your NPTEL website. So the first problem is, or the first question says, the blades of windmill experience cyclic loading and hence must have excellent fatigue properties. So this question is easy to understand. If we have a windmill and we have blades here of windmill. So because this windmill will go under harsh conditions, they will be rotating at high speeds, they will be undergo with various weather conditions, various climate conditions. So they have to be rigid enough to sustain the opposite conditions. So we have to say that due to this cycling loading, these materials or this should have rotor blades should have these properties. It can be either of steel, of aluminum, and its composites. It should be lightweight to reduce the overall weight of the windmill or wind turbine. It should be fatigue resistance. So that is shown. It should have enough strength, enough stiffness, environmentally safe, and able to sustain in lightning, humidity, and temperature conditions. And one thing also, their billet should be recyclable. So we can say this fatigue resistance is under the main criteria. So this statement will be true. Now we'll see the second question. The second question says about beds limit. So the statement is beds limit represents the minimum efficiency that a windmill must have to be commercially successful. So we need to understand first what is the Betts law. So Betts law is simply indicates the maximum power that can be exerted from a windmill. So if you have a windmill, the maximum possible output, this will be governed or this will be given by Betts law. And one more thing, this is a theoretical value. So we need to consider that. So if we follow this statement of Betts law, our given statement cannot be true because in our given statement it is showing that it should be the minimum efficiency, but it is not the minimum. The Betts limits give the maximum efficiency of a windmill. So this statement will be false. Now we'll see the next problem. So this is our third problem. It says in direct type of wind turbines, the tip speed ratio can be greater than 1. So first we have to look at what is the direct type of wind turbines and what is the tip speed ratio. So if you see in this picture, first one is lift type. These are horizontal and these are vertical. So the first one is lift type and second one is direct type. If you see the lift type, they have sharp edges or sharp. their blades are sharp, whereas in direct type, they have a larger surface area or contact area. So they have larger contact with air or with wind compared to lift type. So we'll see what is the tip speed ratio. So basically the tip speed ratio is tip speed of a blade and ratio of wind speeds. So tip speed ratio is given by is the ratio between the tangential speed of a tip, how fast a tip is moving, divided by the actual speed of wind. So basically this factor gives us that how fast a turbine can rotate. So if it is higher, then it can rotate very pretty much high. Otherwise, if it's lower, then it will rotate at lower speeds compared to the speed of wind. So we'll see that for the drag design, this value of lambda is less than 1, or the tip speed is less than wind speed. So from here also you can understand, just because their surface areas are very large, so their speeds are low, but the torque produced will be higher, because overall the energy should be conserved. So the torque produced will be higher, and this torque can be used by using appropriate gear system to harness higher amount of energy. So that is a positive point, or positive point for this drag type system. So come to our actual problem or actual question. So the question says this lambda should be greater than 1. But as we say that for our system lambda is less than 1, or the wind speeds are higher than the tip speed. So this statement will also be false. So now we come to our next problem. So our problem is, or our question is, the blade horizontal axis wind turbines experience uneven forces due to the presence of tower. So we'll see the horizontal axis wind turbines. So basically these are the horizontal type, because if you see the direction, these are in horizontal way. So this will be the horizontal direction. and this is your tower. Similarly, the tower. So if you see the air, if this is the direction of air, this will be even for all whole volume just instant of the area near the volume near the tower. So whenever the wind hit this tower, they will produce some distortion. Similarly, from opposite side. So whenever your blades rotate, they will feel some distortion near the tower. That is the main disadvantage of this two blade type system with horizontal alignment. That is why to mitigate this kind of situation, vertical windmills are can be used. So this statement is true that yes, we face some distortion of we face some uneven forces due to the presence of tau. Next question is modern windmills are made of concrete. So this is very easy to understand that concrete will not be a suitable material for windmill blades because blades should be light and strong. So that is why they are made of metals like steel, aluminum, or their composites. They can never be made of concrete. So this is clearly false. Now we'll see our previous year quiz questions. So now we'll see this question. So this is the formula of calculating wind power. So we need to take this, what is the power? So from your lectures or from your lectures available on the NPTEL websites of this course, if you see, the professor have derived the formula for wind power from a windmill. So since it is being derived there, I am writing it directly. You can refer to the main videos for derivation of this formula. So if we have some system, so this is some blades. We have V1 here, the velocity of or the speed of air, wind, and V2 here. So we need to get this formula. So the power formula will be 1 by 2 rho A V1 square minus V2 square. Where this area is A is area covered by windmill blades. So this is a direct derivation. This direct result of derivation for the power. So we can say that yes, our answer is C, the third. So now we'll see the second question. This that is again related to the Betts law. So it says that Betts limit is maximum efficiency for a wind turbine. According to it, only few the percent of the kinetic energy from wind can be used to spin the turbine to generate electricity. So from the definition, we have already discussed the Betts law is the maximum theoretical power limit. So that can be exerted from the wind, independent of its design, its flow, just the theoretical and maximum limit. So this is not the experimental limit, so this is the theoretical limit. So in this law, Betts concluded that this limit can be highest to be it can be 59.3%. It means only 59.3% of the kinetic energy from a wind can be used or can be converted in electricity. So if we are having some wind, we can only convert the 59.3% of it. It is the maximum theoretical limit. We cannot go beyond that limit, but usually the efficiencies are between 35 to 45%. So our answer will lie on theoretical limit of 59.3%. So our option 2 is correct. So this problem was on the Betts limit of a windmill. Now we'll see the next problem. And next problem is, if V is the velocity of wind, energy available in wind is proportional to what? So from your main lectures, you can say that what is the power of a windmill. If your sweep area is A, which is basically pi r square, where r is the length of the blades, where it resembles the radius of sweep area. So your power is given by half rho A V no, which is power cube. So basically, we can here say that your power is proportional to V cube. So you can also get the energy from the power. So if we remember some basic relations between energy and power, so energy is basically the derivative of power. Or power is, so if you want to calculate, or if you want to get the relation of energy and velocities, you just need to get this relation. So there will be some constant, then v to the power 2, or it will give you simply E is energy is proportional to v to the power 2. So here your option second is correct. Your option 2, E is proportional to v to the power 2 is correct. Now you'll see the next question. That is one interesting question regarding the arrangement of wind wind turbines array. So if you have multiple wind turbines, there are some certain conditions to get the maximum efficiency. So if you just ignore these conditions, if this is a windmill, you will be putting another windmill just as close it can be possible. So if you try to put in that way, there can be maximum number of windmill can be installed in a certain given area. But in that case, every windmill will have its own distortion of wind currents. So if air is being flown in this direction, the windmill A will distort this air, distort this wind and its current. So in vice versa, the windmill B will distort this wind currents. So the overall efficiency will go very down. So we need to have some sufficient gap in between two windmills. So this gap is shown in this diagram. If you have diameter D of the sweep area, or D is just the double of this uh, blade length, so your downwind spacing should be 8 to 12 D, or around 10 times of your D. And your crosswind, it should be around 4 to 6 D. And you should have a sufficient setback distance from any considerable object. So if you arrange your windmills in this manner with sufficient spacing, your efficiency will be highest. So our question says windmills are usually positioned such that the tips of the adjacent windmill touch each other. So this is the first case, it not be correct. Such that the base of adjacent windmills touch each other, so that will also be incorrect. Such that there is sufficient space between windmills to avoid air turbulence from the windmill affecting the adjacent windmill. So this we have discussed in this diagram. So third statement will correct. Also see the fourth statement, such that the gear of the windmills touch each other, that is completely incorrect. So our option third is correct for this condition. So we should have sufficient spacing to avoid air turbulences. Now let's see the next question. So this is our question 6. Question 6 says the gearbox is used in windmill to typically ensure what? Uniform RPM of blade and generator, higher RPM at blade, lower RPM at generator, lower RPM at blade, higher RPM at generator, or no RPM at blade but low RPM at generator. So we'll see first what is the gearbox and what are the uses of gearbox. So basically, if we see this wind turbine, our gearbox is situated here. So that is basically between the generator and rotor. So let's say it is between your rotor and generator. So what is a gearbox? A gearbox is basically combination of two discs. This, let's say A, first is A and second one is B. So they are having difference in their diameter. So they are connected by teeth. So in such a manner, in such a combination that if one disc rotate, another will also rotate with that. But due to the difference in their radius and their radii, rotation speeds will be different for is going to be different. As these rotation speeds are different and due to the energy conservation law, something will also be different. So our torque will also be different. So if your larger disk rotates your smaller disk, if V1 is VA is for rotation speed of smaller disk and VB is rotation speed of. So in such a case, because their diameters are and their circumference are different, so for a single rotation of disk B, there will be multiple rotations of disk A. So if this is looking like this, it's let's say it's rotation 1 will give you the 40 dates rotation 2. So speed of or the rotation speed of smaller disk will be higher, whereas the torque will be lower. So these gearbox are basically used to match the generator frequency from the rotor frequency. So if rotor is since these are tunable gearbox or their ratios can be controlled. If rotor speeds are higher, they can reduce them down to the generator speed. If rotor speeds, rotation speeds are quite lower, then they can try to match, they can match the generator speed for the optimum range. So we need the generator speeds to be constant because we need the electricity produced should be at 50 hertz. So we have to ensure that the generators are always rotating or the generator shafts are always rotating at between a certain rotation speed. So where this role of gearbox come? So in most of the cases, the rotors or blades, rotors, this hub is rotating at lower speeds because they are very large in size. So they will be taking few rotations in a minute. But you need 50 hertz, 50 hertz of frequency or 50 rotation per second. It is not easy to give 50 rotation per second for this size of rotor. So it can be lower than 50. So just to increase the rotating speed, we have to use this gearbox system. So our answer will be lower RPM at blade and higher RPM at generator. So by this, we will get the optimum frequency and the optimum speed. So this was your question 6. We will be looking at question 7. So it is like select the statement which are true. So A is tip speed ratio is the ratio of linear speed of the tip of the blade to the wind speed. So basically this is the ratio of tip versus wind. So yes, the statement is correct because as we have already discussed, what is the tip speed ratio? Is the ratio of velocity or the speed of blade tips can be the tangential speed divided by the speed of wind. So the second statement is speed ratio is greater than 1 for push design and smaller than 1 for the lift design. And the statement C is the opposite of that. So we know for the lift design, this is the lift design and this is the drag design, or you can say it is a push design. So we have already discussed that in the lift design, they have sharp edges, but in push design, they have larger area, the contact area. So in that case, in the case of lift design, your wind tips will be, your speed of your tips will be higher than your wind speed because they are very sharp. So that is why they will be moving faster than the wind. And where the drag design, they are bulkier than the lift design and their surface area is higher, so they will be interacting more. So their velocities or the speeds of tip will be lower than speed of wind, but their torques will be higher. So our second statement will be incorrect, but our third statement will be correct. And for this, the speed of blade is more at the center than the tip. So you take whatever design, whether it be horizontal or vertical, your speeds are always higher. This is if this is V center and this is the V edge, this is always higher. It is clearly understandable that edge speeds will be higher than the center speed. So that is also incorrect. So our statement A and C is correct. Now we'll take the next question. So as we have some time, we can take a break of 5 to 10 minutes and then we will be coming back. Okay, so we are back. So we will look at these remaining question. So our question 8 says, what is the significance of three blades in windmill? So you have given three options. One is, in comparison to one blade, three blades are used to increase the interaction with wind. B is the better suited for generating higher torque, and C distributes the load of the shaft more uniformly than the one blade windmill, especially with respect of wind turbulence near tower. So this option C is clearly understandable, that if you have only one turbine, if you see in this image, this the first turbine, so it will generate an immense amount of torque wherever the blades is moving. So if you have only one blade, it will be very less its efficiency will be very less. Also, it will generate a very large amount of stress on overall windmill structure. So that is not very optimum for windmills. The next one is the two blade system, but in our previous question also we have already seen that these two blade systems are also affected by your this main shaft. So because your wind current or air will be distorted near this main shaft, so overall production of electricity will be affected, and your tow rotor system is also not the optimum condition or the optimum design for your windmill structure. So this kind of, to mitigate this kind of effects, we move to the three blade systems. So in this picture also, in this animation, you can compare for the same surface area, you will be need very fatter blade for a single blade system. So you can make this three blade system. You can make it skinnier or slimmer, as well as you can make it slower, because having same sweep area and having same rotation for a specific for a given wind speeds, your single blade system need to be rotate at very high speed or thrice speed as compared to your three blade system. So these are your rotating speeds. So in that case also, your three blade systems are considered. So you can go for the four blade system also, but the three blade system is the most efficient and mostly used for windmill system. So your all three options are correct for this question. Then we will see the next question. So this is question 9. It says horizontal axis wind turbines access stronger winds are often mounted on tall towers, usually have blades that are pushed by wind for only part of the rotation, captures wind energy throughout rotation. So we can say that this is your vertical type, this is your horizontal type wind turbine, and this is your vertical type wind turbine. So in this, these are push type wind turbines where your blades are not sharp, but you have a very large surface area or the large contact area with air. So due to a large contact area, you will have lower velocity, lower speeds, but higher torque. So by this advantage, you can make them in smaller dimensions. So that is why they can be mounted on the towers, or you can even mount them on buildings, towers or buildings. So whenever you see the small scale wind turbines, these are mainly preferred as the vertical type wind turbines because their efficiencies are quite higher for the lower size. So for this rotation, throughout the rotation, they capture the wind energy, correct? Because for the original type of system, they need to be aligned in this direction of wind. But in this rotation, in this vertical type of system, wherever your wind comes, they will rotate this wind turbine. So you don't need to use a system to change the direction of your axis or your rotation. So it will again make it lighter and more convenient for small scale users. So option A is also correct. They can access stronger wind in any direction. They can be used in towers or buildings. But the option 3, which says usually the blades that are pushed by the wind only part of their rotation. So that is not the correct. So all three are correct. So now we'll see the next question. So its question asks where and why is the pitch bearing used in windmill setup? So first we need to understand what is the pitch bearing. So if you see this windmill, this is your main hub, this is your gearbox, this is your generator bearings, this is your rotor, and where the blades are attached with the rotor, that is called your pitch bearing. The pitch bearing also shown here. So pitch bearing is basically made up of multiple rings. So this ring is attached with rotor and this ring is attached with your blade. So if you understand by pitch, so that is these pitch bearings are used to align this direction of blade. So if you can change this direction or slightly rotate the blade, that is called changing the pitch of blade. Okay, so you have to make a system of multiple rings that these blades are independent to move. So according to the direction of wind, direction of airflow, they will adjust, the blades will themselves adjust them, and it should be also adjusted externally to get the maximum drag or maximum efficiency for rotation. So basically these are the pitch bearing. So option A is, first option is blades are attached to it. So yes, one end blades are attached. Hub and blades are linked using this. So that's also correct. We have already seen that hub, or this is the hub. Hub and blades are attached. These are blades. So they are connected, linked. It reorients the blade. So yes, this is your reorientation represented by this arrow. So that is also correct. It increases the RPM. So we can say from here, because RPM is independent of the pitch of any blade, so it will not affect the RPM. Only the pitch can be controlled by the pitch PL. So option 4 will not be correct. So all option 3 are correct. A, B, and first, second, and third. Okay, so these were the questions for today. As we have half an hour more, so this time is for our discussion. So if anyone have any doubts in this week 8 course content or whatever questions we have discussed today, so you can just ask. I will be here for 30 minutes around for up to 9 p.m. So if you have any queries for this content or previous content, you can let me know.